welcome back to the second lecture. My course is about Lambda-adic forms, and in the first lecture I actually gave two examples of Lambda-adic forms. I thought it would be better to give some examples first before giving the formal definition. Today we will go over the first example in much more detail. I will define formally what a Lambda-adic form is, and I will show that the Eisenstein family that we looked at, the p-adic family of Eisenstein forms, is actually a Lambda-adic form. Okay, so that is the goal today, and the fact that all those Eisenstein series were congruent to each other mod p will come out of the wash. I may forget to say why that's true, because a Lambda-adic form is a slightly more general object than just a lot of modular forms being congruent modulo p, but you can ask me if I forget to say why all the forms are congruent modulo p at the end. So let me recall some things. I wasn't planning to do this, but I think it's good to do this. So yesterday, we had, okay, maybe I won't recall everything. I'll just recall the sort of generalized Eisenstein series for weight k greater than 1, n greater than 1, and chi a character. So p is prime to n. This was a Dirichlet character, integer, which is co-prime to p, and this was a Dirichlet character. So I defined this Eisenstein series ek chi to be get the rotation right. Yeah, to be L1 minus k chi. It is of course defined by some sort of averaging of gamma naught n modulo gamma infinity, the stabilizer of the cusp infinity, over so 1 over cz plus d to the k with some chi of d and things in the numerator. So it's defined in some explicit series. That's why it's called an Eisenstein series. But I'm writing straight away here, instead of giving the original definition, I'm writing straight away its Q expansion. Okay, and we all know this is the sum d dividing n chi of d to the k minus 1. And this is the Dirichlet L function attached to the character chi. So notice here I'm taking characters of a special kind. Well, they're not that special actually, because this is more or less a random conductor, right? There's a prime to p part, which is n, and there's a p part, which is p to the r. So that's, every integer can be written like that, except that I assume that r is bigger than or equal to 1, but that's not important here. I can assume r equals 0 also for now. Later r will be bigger than or equal to 1. So this number, the special value of the Dirichlet L function at negative integers, is given like this. Okay, so everything is very explicit here. This was the Eisenstein series, the basic Eisenstein series, and we said that if you want to do p-adic families, you need to p-stabilize. Remember the Eisenstein E2, which came up in Professor Gun's talk from a few minutes ago, was not a modular form. It was a quasi-modular form. But the p-stabilization actually turns out to be a modular form. You can recover the holomorphy by taking a difference of two old forms. So more generally, in this setting, you have the following p-stabilization. Okay, so this is the p-stabilization of this particular modular form. You take a difference of these two old forms. So this is not doing much if the conductor of chi is divisible by p. I mean, if this chi has a genuine p part, this chi of p is 0. So this term is not there. You just get the original thing. But if chi was really of level n and there was nothing in the p part, then this is some non-trivial thing. You're subtracting off something. Okay, so that's the P stabilization. And this was a modular form in of weight k and level np to the r chi. And its Q expansion is very similar to the one above, except it's P deprived. So some of the Euler factors go away, etc. So let us write the background noise. If you could shut your mics off, that would be great. To the n, sum d dividing n dp equals 1, chi of d, d to the k minus 1. And this is, well, you can almost guess what this is. It's the difference of these two things. So what happens to the constant term? It becomes this. Okay, so that is the basic fundamental Eisenstein series that we want to start with. Notice you cannot do p-adic families if you don't have general levels and general weights, etc. But most importantly, general levels. You cannot do p-adic families for level 1. So it's very important to understand this. People like to simplify problems by working in level 1, but for p-adic families, p is in the level, for instance, and then sometimes high powers of p go into the level. So you really have to look at all levels at the same time. Okay, so I made this remark yesterday. Let me say it again today. Remark, if p divides the conductor of chi, and I just said it right now, this ek chi p is equal to ek chi, right? Because this term is not there. Okay, very good. So this was from my yesterday's notes. So now I can finally start the definition of a lambda-adic form. Maybe I will go to another page. Any questions so far? This was just a review from yesterday. Can you see the, did I go off the page again and things, off the screen? I hope I wasn't looking. I hope I didn't go off the page. I wasn't looking at the screen. So that, yeah, everything is there. Great. Okay, so lambda-adic forms. So, so far P could have been 2 also, but here I will now assume that P is an odd prime. Maybe I did that yesterday also, I can't remember. Anyway, P was 11 for in the examples. But in this generality that I want to do today, for p-adic families of modular forms or lambda-adic forms, there's a P hiding in lambda, I'll explain in a second. I want to assume that P is odd. If P is equal to 2, you replace P by Q equals 4. Okay, this is the standard trick in number theory. Many theorems which are false for P equals 2 suddenly become true for if you replace P by 2 by 4. So maybe the prime numbers are 3, 4, 5, 7, 11, not 2, 3, 5. This is something that comes up if you study number theory a lot, especially Iwasawa theory, and try and deal with the prime 2. And there are entire papers about this, but I won't get into that now. So n is going to be an integer, which is co-prime to P. This is what we call the tame level. P is the wild level. Psi will be a fixed Dirichlet character, but of level NP, okay? So there's some conventions here, and it takes a little bit of getting used to. So this will be the character of the p-adic family. Notice not a character of level n, it's a character of level np, and not np to the r. The np to the r will come in a second. Omega is this character I defined yesterday, very quickly. So this is the mod p cyclotomic character. So what was this character? Given an integer a, co-prime to p, you map it to the unique p minus first root of unity. This group is isomorphic to the group of p minus first roots of unity. So abstractly, it's isomorphic to that. So but you choose an appropriate p minus first root of unity such that if you go mod p, you recover the original integer a. Okay, so that is the mod p cyclotomic character. It's everywhere in the literature. And finally, for a p power root of unity zeta, my zetas are not very good, but these things are zetas. This is a wild character. This is a tame character. This is a wild character. And it's defined in the following way. So since it's wild on the tame part, on this group, you know, for p odd is a cyclic group. I'm sure you've learned this in your algebra classes. For p and odd prime, z mod p to the r is a cyclic group, but you can still write it as its p part and prime to p part as in this way. So on the tame part, you just make it act trivially. It's the trivial character on the tame part. But on the wild part, so here 1 plus p is a generator. On the wild part, you map it to zeta, which is a p power root of unity. And I take it this way. I let r be greater than 1, and I write p to the r minus 1. So it's appropriate to do this because you see there's an r minus 1 here and r here. And it's more convenient to have the r here than having r plus 1s here. So if I had taken a p to the r here, I'd have to put r plus 1 here, which is a bit annoying. So p to the r here forces you to take a r minus 1 here. Right? So when r, for example, when r is equal to 1, then this is just the trivial zeta is 1, and then this is the trivial character when r is 1. Okay, so these are some Dirichlet characters that I will be looking at. These are the Dirichlet characters. These are some integers. And finally, I will let most important definition perhaps of today, lambda, this is where lambda-adic forms are coming from, be, by the way, I'm wearing a microphone today. I hope the audio is a lot better. Anupam?
Yes, yes.
Okay, good, Rupam. Thank you. My mic is right below my chin now. Yesterday I was screaming across the desk. My laptop was a little far away. Okay, so lambda is ZP power series X. So this is a power series ring in one variable X. X is a formal variable. And these are the p-adic integers. I hope all of you have seen this before. I cannot spend 3 or 4 lectures recalling all the properties of p-adic numbers. But p-adic families of modular forms definitely use properties of p-adic numbers. So you'll have to refresh what things like ZP and QP and things are. Okay, so ZP is the ring of integers of QP, and QP is the p-adic completion of Q under the p-adic metric. 2 numbers are close if they're highly divisible by p. For example, in the 5-adic metric, 125 is very close to 0. So you complete Q under this metric, you get QP, and the things with norm less than or equal to 1 are the unit ball is ZP. So it includes Z, for example. It's a completion of Z, the p-adic metric. Okay, and then I will be the integral closure of lambda in K. Well, what is K? K is going to be a finite extension of the quotient field of lambda. Okay, so lambda is an integral domain. That's a nice exercise to do. So this is a domain. So you can look at all fractions of power series and you get a quotient field. You can take a finite extension of that field, and then you can take the integral closure of lambda in K. Now, if you didn't like all of this, well, you could very well just think of K to be equal to the quotient field, and then I will become lambda. But if you want to define a lambda-adic form in complete generality, and I think I should do that today since I didn't really do it yesterday, then you do have to take these finite extensions. This is the analog of having your Fourier coefficients of your modular form in finite extensions of Q, not always in Q, but they're in finite extensions of Q. So similarly, lambda-adic forms take values in finite extensions. And they don't really just, when the good ones, the primitive ones, as I'll define soon, take values, have integral Fourier coefficients. So this is the integral closure of lambda in Q, in K. Definition. A lambda-adic form, or more precisely an I-adic form, but I will write to just save a little bit of notation. So this is really an I-adic form, but a lambda-adic form, when I is equal to lambda, of course, they're the same thing. of tame level n and character psi is a formal Q expansion. Formal, okay? No holomorphic thing. It's just defined by a Q expansion. This is p-adic stuff, so you cannot have holomorphicity, etc. So it's a formal Q expansion like this. But this time, the Fourier coefficients are not algebraic numbers, but they're power series. A and F are actually in I, okay? Such that, and unfortunately, I have to go to the next page. So remember that F was a formal object. It's a formal Q expansion. So Q is just a thing which shows you that you have a Q expansion, and A and F are the nth Fourier coefficients, generalized Fourier coefficients, but they're power series, they're not numbers, such that for all arithmetic specializations, so what does arithmetic specialization mean? This means that if you take a homomorphism, a ZP algebra homomorphism, from I to QP bar, which is of a very special kind. So when you restrict this homomorphism to lambda, which is therefore also a map from lambda to QP bar, it should take X to something very concrete. I'll just same stuff as before. So on lambda, remember lambda was ZP power series X. So this homomorphism is completely determined on what happens to X. It's a ZP algebra homomorphism. ZP goes to ZP, but X may go anywhere as long as your power series converges. So we take some standard elements which show up in Iwasawa theory. For example, forget the zeta for a second. Assume that R is 1, then this p to the r minus 1 root of unity is just zeta is 1. Then this is quite simple. It's just 1 plus p to the k minus 1. If you expand this using the binomial expansion, we'll start with a 1, but you're subtracting the 1, right? And then everything here, therefore, will be divisible by p. So when everything is divisible by p and you specialize in the power series, as you take higher and higher powers of x, you'll get higher and higher powers of p, and so the power series will converge p-adically. So you'll get a genuine number in ZP. Okay, when you specialize at x goes to 1 plus p to the k minus 1, you get a genuine number in ZP. But you could do something a bit more complicated. You could also take a p power root of unity with this appropriate normalization and pre-multiply your 1 plus p to the k by zeta. Now, if you've done a little bit of algebraic number theory, and even if you haven't, if you just think about it a little bit, these roots of unity are actually congruent to 1 modulo p. Okay, so think about that. That's a nice exercise with cyclotomic polynomials maybe and things like that. But the p power roots of unity are actually, they cut out totally ramified extensions. The residue fields are the same as FP, and they just map to 1. They're trivial. So this is, when you multiply this 1 plus p to the k by zeta, you still get a number which is congruent to 1 mod p. It doesn't change the congruence class. And when you subtract 1, it's still divisible by p. So this will still converge. But it won't lie in ZP anymore, it'll lie in a finite extension of ZP, and so therefore we write QP bar here. Okay, so such that for all arithmetic specializations, these homomorphisms which restrict on lambda to these very special homomorphisms, these are called arithmetic specializations of I, specializing the variable x basically. Okay, such that for all arithmetic specializations of I, nu, which lie over the nu k zeta, by the way, there are finitely many nus which extend a particular nu k zeta. Since this extension is finite, there's not much you can do here. So on this base, it's completely determined, and then there's finitely many options here to extend to nu. Okay, I think I said too much there. Such that for all arithmetic specializations, f nu, which is by definition, you apply nu to f, which is by definition, you apply nu to all the power series in the Q expansion, which this time is a Q expansion in this ring, right? Because the A and Fs were in I, but once you apply nu, then they wind up in QP bar. So these things, and there are infinitely many of them, because for each k greater than 2 and each zeta, p power root 2, there's a two-parameter family for weight k and weight zeta, is the Q expansion of a classical modular form of weight k greater than 2. Okay, so you can read off the weight, level, and character of the form that you get after specialization from the data of the specialization. Notice the specialization had a k and a zeta. So weight k greater than 2, level np to the r, right? There's an r here because of the root of unity. Notice that because r is greater than 1, there's always a p in the level. And character, chi, which is psi, which was the original fixed character, a tame character which rotates and depends on k, and a wild character which was zeta, chi zeta. That's why I introduced these characters up at the beginning, because I thought you might get a little confused if I suddenly put them in. Remember from the previous page, these were the characters that we first talked about. We had the mod p cyclotomic character omega and the wild character chi zeta. So as you vary the weight k, this character rotates, and as you vary zeta, this character changes. Okay, and then there's this fixed character psi, which is the character of the lambda-adic form. Okay, so in other words, this is an element of mk, i.e., f nu belongs to mk npr chi, where chi is given by this formula. Okay, so this is quite a mouthful, but it is, I wanted to give the proper formal definition with no exceptions, at least for p odd. But basically, what is it doing? It's basically a formal Q expansion, such that when you specialize at some x at something, you get a classical modular form. And there are infinitely many specializations, you get infinitely many modular forms. Maybe now is a good time to say why all these modular forms are congruent modulo p. So for example, if you take zeta to be 1, which is what I was doing yesterday, I didn't have any zeta, I just had weights k. If you look at this homomorphism modulo p, then it's the zero homomorphism, right? Because p is 0, so this is 1 to the k minus 1, so it's 1 minus 1, which is 0, so x is going to 0. So all these homomorphisms specialize to one particular homomorphism. So mod p, you get the same modular form. Okay, so this is why this is a slightly, I won't say vast generalization, but a generalization of the examples that we were doing yesterday. So far, so good. Any questions? Everyone understands the definition of a lambda-adic form?
Sir, so the F1, F2, etc. yesterday were just these F news for different news. Is that correct?
Exactly. F1 was actually, maybe I can call this even more precisely, Fk zeta, and then, so this is a little imprecise because it actually depends on nu, which is a finite extension of this. But if you take zeta to be 1 and you take k to be 2, 3, 4, 5, then this f nu 2, 1 is just f2 from yesterday. And f nu 3, 1 was f3 from yesterday, and so on and so forth. Okay?
Okay.
So yesterday I had taken the zetas to be 1. Okay, so let us move on. So now we can finally define what it means to be a Lambda-adic Eisenstein series. Eisenstein. Okay, so I will say it again explicitly many times because I want to do one example. We explicitly construct today a Lambda-adic Eisenstein series, a Lambda-adic form, which I'll call E psi. Psi was that tame character. Interpolating, this is an interpolation. So under specialization, you get some modular forms. That's like an interpolation of all those modular forms. Interpolating the Eisenstein, the classical Eisenstein series, P stabilized Eisenstein series, which I recalled at the beginning of this lecture today. We were done yesterday in more detail. E k chi p belonging to m k n p r chi. And chi, remember, was psi omega to the minus k chi zeta. This formula you'll get very used to. It looks very complicated at the beginning, but actually, by the way, this is a completely general decomposition of a Dirichlet character. So it's not something, if you're forced to do this, because if you have any character of conductor M, there's an N part and a P part. So psi takes care of all of the N part, but there's a small P part in psi, which may not be arbitrary, but you can rotate the K here to make this completely any arbitrary character on the P part with these two data, because of the wild part and this omega is the tame part. And here the tame part of psi was fixed, but omega is changing. So this has an arbitrary tame part and chi zeta is wild. So this is actually the decomposition of any Dirichlet character in the p-adic world, or any character of conductor n times p to the r. So this is kind of forced on you. So it's not something to be scared of. Okay, so constructed yesterday and recall today. Okay, so this is the goal today. So let us do this now extremely slowly. So I will do this so slowly because, I know that not everyone is familiar with p-adic numbers. So, and especially raising power series to p-adic exponents and things like that, it can be a little scary at the beginning. So I'll recall some things, but maybe not everything. So if S is a p-adic integer, it makes sense to speak of the following power series. I need this power series because I'm going to construct a lambda-adic form, so I need some special power series. So here is a very interesting power series. I'm going to define this power series 1 plus, for example, if S is an integer, because, right, suppose S is 5, then of course 1 plus x to the power of 5 is very clear what you do, use the binomial expansion. But if S is a p-adic integer, then you can just use the binomial theorem and write down the following object. Okay, so this is a power series. You can see there's an x here, and now there's this strange S choose M here, but S is a p-adic number. Okay, but I'm claiming that if S is a p-adic number, then the binomial coefficient S choose M is another p-adic integer. If S is a p-adic integer, then S choose M is another p-adic integer. Okay, so of course you know that for regular integers, if you have an integer like 5 and you do 5 choose 0, 5 choose 1, 5 choose 2, of course you will get just integers, and so this will make sense. But if S is a p-adic integer, then what do you do? Well, it turns out that this is a polynomial, right? If you just let S be a variable and M be fixed, then there's just a polynomial, right? S minus 1, S minus 2 to S minus M plus 1 over something factorial, M factorial or something. It's just a polynomial. And it takes integers to integers, that polynomial, even though it seems to have a denominator. So, and polynomials are continuous. So if you have a p-adic integer, which is a limit of regular integers in the p-adic topology, then you will get a p-adic integer. You will get something in the closure of this, closure of Z, but ZP is closed. So you'll actually wind up getting something just in ZP. Okay, so that small argument shows you that even if S is not really a genuine integer, but a p-adic integer, then this binomial coefficient is a well-defined p-adic integer. And therefore, you get something in this power series expansion. Okay, so these are the kind of comments maybe I'll spend a little bit of time on, but I won't be able to spend too much time on. Most people would just write this down and say that this is just obvious, that this power series exists in ZP power series X. Okay, so here is something else that I would like to note. So here's one note. Get my whiteout. Second thing is that if D is congruent to 1 modulo P, then it is possible to write every integer which is congruent to 1 mod P as a power of 1 plus P. Then D is equal to 1 plus P to some S, which I'll call S of D, for some p-adic integer in ZP. So this is another little fact from the p-adic world. The group 1 plus P ZP is a topologically cyclic group, and it's generated topologically by this 1 plus P element. So that means 1 plus P to any power gives you this D. Okay, so I'll use this again and again, that you can raise 1 plus P to a p-adic integer to recover any regular integer which is congruent to 1 modulo P. Okay, so if you like logarithms, then you can define S of D explicitly as log of D divided by log of 1 plus P. But then you have to talk about the p-adic logarithm. So let us not get too much into that. Okay, finally, with these two notations, let us set AD of X. So this is a power series now, which uses these two facts. It's basically 1 plus X to the S of D. Now these two make sense, right? Because given a D congruent to 1 mod P, then S of D makes sense, and then 1 plus X to the S also makes sense. But I normalize things a little bit by dividing by D. This is okay to do because D is co-prime to P. It's congruent to 1 mod P, so 1 over D is actually a p-adic integer. Even though it looks like it has a denominator, it's actually a p-adic integer. So this is still in lambda by the above facts. And I'll remind you again and again that this is ZP power series X. After a while, I'll stop writing that. So why did we look at this? Well, here is a very nice observation. A note within the note. AD, if you specialize at 1 plus P to the K minus 1, these special elements, well, what happens? You get 1 over D. You put X to be 1 plus P to the K minus 1, the minus 1s cancel, and you get 1 plus P to the K S of D. But remember, 1 plus P to the S of D was D. So this is magically D to the K minus 1. Because you're dividing by this D. Right? This is just D to the K, and here you have 1 to D. So I'll pause here. So these are the kind of tricks that you have to do when you're doing p-adic interpolation. Okay? Now I hope you can understand why I'm trying to interpolate D to the K minus 1. So here we've already come up with a power series which interpolates the integer D to the K minus 1. So now what do you do if D is general but co-prime to P? Because remember, we had sums over D dividing N, D co-prime to P, chi of D, D to the K minus 1. So what do you do if D is co-prime to P in general? Well, if D is co-prime to P, is a general in positive integer, then we use the following decomposition. We write the units of the p-adic integers. We break them into their tame and wild part. And we do this using some notation. So I'm calling this omega D. So omega D sometimes is I realize now, I should have realized this earlier while preparing these talks, that omega d is sometimes a p minus first root of unity, which is the image of d under this thing, but sometimes it's just the component here. It's actually an element of z mod p star. So omega d, so this is a definition, comma, diamond of d. So you can decompose any integer which is co-prime to p into its tame part, its z mod p star part, and its 1 plus pzp part, and we write them individually as omega d and diamond d. Okay? So these are the things that we know how to do something for, because they're congruent to 1 modulo p. But we've pulled out the omega d part here. Okay, and we define set. Now we have to define AD in general. In this case, we define AD of x to be, well, again, 1 over d, because we want to get the d to the k minus 1. 1 plus x s. Now the thing is, you don't know how to, we don't know how to define s of d. Okay, s of d only makes sense if d is congruent to 1 mod p. But this diamond d is congruent to 1 mod p because it's in this part. So we define it to be s of diamond d. Okay. So diamond d is not necessarily an integer anymore. It's the prime, it is some p-adic integer, which is the wild part of d, which is a genuine integer. That's the diamond part is the wild part of d, which is congruent to 1 mod p. It's a p-adic integer. And then this formula, I didn't really say that d was an integer. This works for any d in zp, which is congruent to 1 mod p. So we have this. Okay, now this looks a bit complicated. That's why I did all these steps before, but I could have gone straight to this step. But now let us actually do the same computation we did up here and look what happens under specialization. So if you specialize x at zeta 1 plus p to the k minus 1, well, what happens? You get a 1 over d. Now x is this whole thing minus 1. So the ones will cancel, and you will get a zeta s of diamond d and a 1 plus p to the k s of diamond d. Oops, something went off the page. So I hope you can see that. I should be writing bigger here. So all I did is I specialized 1 plus x at zeta 1 plus p to the k. In other words, x at this thing minus 1. Okay, so this is just plugging in, and that's a definition. But now I'm claiming that this is the same as 1 over d chi zeta of diamond d. Why is that? Well, diamond d was just using this property over here, but for diamond d, using this property over here, but for diamond d, this is 1 plus p to the s of diamond d, the stuff inside the bracket. Right? And chi zeta took 1 plus p to zeta. So this is exactly this. I hope you understood that little computation there. I'll say it one more time. Diamond d is 1 plus p to the s of diamond d, because you can write any p-adic integer congruent to 1 mod p as a power of 1 plus p, and the power is s of diamond d by definition of s. And then chi zeta of 1 plus p was just zeta by definition of chi zeta. So 1 plus p to some power goes to zeta to that power. And here we get just 1 plus p to the s of d, which again is diamond d by definition of this to the k. Okay, so this was the same thing, but inside a little bit easier, because 1 plus p to the s of d was just diamond d. And now I can write this, and unfortunately it's gone to the bottom of the page. I hope you can still see. This is extremely important. It's the end of the computation here. Minus omega sorry, omega to the minus k of d, chi zeta of d, d to the k minus 1. Okay, so I'm maybe skipping a step here. What is diamond d? Diamond d, d is equal to omega d times diamond d. Okay, so diamond d to the k is just d to the k omega minus k to the d. So that's where the omega minus k to the d came. And then you get a d to the k, so that's the d to the k here. And then I divide it by 1 over d, so you get d to the k minus 1. Is any questions up for this computation? So now we've constructed a power series a sub d for any integer co-prime to p, which has the property that when you specialize at zeta 1 plus p to the k minus 1, you get this particular integer, d to the k minus 1. And notice that these are beginning to look like the characters that we eventually want to. There's omega minus k, chi zeta. There's still no psi here. We still have to do a little bit more, but we've come up to, we're getting close. We want to actually put chi of d here, and we've come so far. Can I flip the page?
Yeah, sure.
Okay. So finally, for psi, which was a character of level np star to c star, define a and psi. Now I'm writing small a's because I wanted to match Fourier coefficients. D dividing n, dp equals 1. So we want to get a psi into the picture, right? So far there were no psis. And we had defined AD for all integers co-prime to p, so we just put that here. And now this is an element of no longer ZP, because the values of psi interfere. So it's a slightly bigger ring than ZP, power series X. Let me call this ring I sub psi. This is a finite extension of lambda, right? It's one of those rings I that come up and they're unavoidable. You cannot always work in lambda. You might have to go to a finite extension. So again, let us compute a little bit now what happens when you specialize at zeta 1 plus p to the k minus 1. If you take x to be that, well, we already specialized this, so you just get, just copying from the previous page, omega minus kd, right? This specialized to omega minus kd chi zeta of d, d to the k minus 1, which I hope you recall was exactly sigma k minus 1 chi, p deprived because d was co-prime to p of n. So these 3 or 4 steps that I did show that it is possible to construct a power series not in lambda, but in a slightly bigger extension than lambda, such that when you specialize at zeta 1 plus p to the k minus 1, you get this particular sum of divisors function with, of course, chi to be psi omega minus k chi zeta. Okay, this is always true. Psi omega minus k chi zeta evaluated at d. Okay, so we get exactly this. So to summarize, so we have succeeded in interpolating the non-constant terms of the p-stabilized Eisenstein series Ek chi p. Okay, so to interpolate the constant terms, we need to find another power series A0 psi of x belonging to I psi, which is ZP psi x, such that A0 psi of zeta 1 plus p to the k minus 1, the standard specialization, is the p deprived Dirichlet L value. Okay, so this was not the Bernoulli number minus bk chi divided by 2k, but there was an Euler factor in front, 1 minus chi of pp to the k minus 1 in front of that generalized Bernoulli number. Now this looks extremely tricky because Bernoulli numbers are quite random looking objects. And so here we were lucky, divisor functions, etc. Maybe even some clever high school student could have done this. But this really requires the work of some sort of geniuses. It turns out that there is, in fact, a power series which interpolates periodically the Dirichlet L values. And that is the Kubota-Leopold p-adic L function. Okay, so it was written down by Kubota and Leopold, who showed that such an interpolation in fact exists, such a power series exists. And later Iwasawa actually showed that the power series has some nice analytic properties. And it's essentially entire as a p-adic variable and things like that, except when chi is trivial, but we won't assume chi is trivial maybe in this talk. Yeah, so that unfortunately requires a whole course in Iwasawa theory, but I hope this particular lecture will motivate you to learn some of this material. Unfortunately, there are very few people in India who study this and know this, and I'm hoping that this will motivate you to do this. Okay, so how do we find such a power series? So let me give you some background on it. So to do this, need to introduce the Kubota-Leopold p-adic L function. Okay. So unfortunately, I have to go to another page after writing the title. Shall I flip the page? Any questions? Okay, I don't hear anything, so I will move on. So I'll do this in a bit of generality. So for a moment, let us just work with some general notation. So let chi be an arbitrary character. Okay, but let us assume it's even, arbitrary Dirichlet character. But even means chi of minus 1 is equal to 1. And let us assume that chi is not 1 for simplicity. Because as I said, there's some analyticity issues, simplicity about the poles of that p-adic L function. So assume that chi is not 1 for simplicity. Then there does indeed exist a continuous, even analytic function, LPS chi. Now this is a lower p, okay, on the extended disk. So these are the complex p-adic numbers. This is the p-adic norm. So I could have just put here norm of SP less than or equal to 1. But if you like to be precise, then in fact, this is a little bigger than the usual unit disk. Okay, it's kind of, here's the unit disk, radius 1. So a norm of S less than or equal to 1. This is a little bit bigger, this radius. So there's this a continuous, even analytic function such that if you specialize this at 1 minus k, So 1 minus k, k is going to be an integer. 1 minus k is also an integer, and integers always have norm less than or equal to 1, so they're here. So 1 minus k is here maybe inside this norm less than 1 disk. You get exactly the Dirichlet values, but with some Euler factor removed. And it's the Dirichlet value of the Dirichlet function corresponding to the character chi to the omega minus k. So as you keep moving the k around, your character here rotates a little bit. Notice omega is periodic, right? Omega to the p minus 1 is 1 because it's a character of z mod p star. So this keeps rotating. And this is the remarkable formula which I'm now using as a back blocks. There is in fact a continuous function or even analytic function on this disk which gives exactly these Bernoulli numbers with some fudge factors removed for all k greater than 1. Moreover, so a reference for this is maybe if you just want this naive, let me give some references as I go along, since I'm not proving things but using this as a black box. C.F. Washington's book, Theorem 5.11. Washington's book on cyclotomic fields. And I'll write all the references down at the end. Moreover, there's a theorem of Iwasawa, which is also essentially in Washington's book, 7.10, that this is an analytic function in the following sense. There exists a unique power series G chi x belonging to I. This is a bit general now because, right, chi was an arbitrary character here. Zp chi x such that if you go back to this S, but instead you put 1 minus S here, you get this particular power series evaluated at so there's a power series in X, this particular power series, that when you put this particular specialization in, this is for S belonging to ZP, let's say, but actually even in this disk, but let's take S and ZP or something. The ones cancel, you get something which is divisible by P, so the power series will converge, and you get actually this particular value. So this is a bootstrapping up of the Kubota-Leopold p-adic function, because this is just a interpolation of some Bernoulli numbers. But now we're saying that they in fact all come from one particular power series. There's one particular power series in X that when if you do some specializations like this, you get the p-adic function, but with 1 minus S here. Okay, so this reference in Washington actually has both S's here, but I've changed it a little bit to put S here and 1 minus S here. Okay. Moreover, the second part of the theorem of Iwasawa. Moreover, it turns out that if you look at the power series for chi times chi zeta, or if you multiply by a wild character, then you get exactly the power series of chi, but shifted like this. Enough brackets? Maybe not. Yes, I think I have enough brackets. Okay, so these are two little properties I'm going to use of this particular p-adic function. First of all, it comes from a power series, and secondly, if you just move your character by a wild character, then it behaves like this. Okay, so far I think I have everything that I need about the p-adic function. So let us go back to the constant term of the Lambda-adic Eisenstein series that we're trying to construct. So set A0 psi of x to be a half G psi of x. Okay, so from the Kubota-Leopold periodic function, we are applying this with chi. We're applying this with, now this is all general. We're applying this with chi to be psi, and we let A0 psi of x to be half G psi of x. So this is just an ad hoc definition for now. Now let us see if this really works out. So some nice computation will show this is exactly the right thing. So can I flip the page? Any questions? I got a thumbs up from somebody. Okay. So here we are going to do a small computation. Then A0 psi of zeta 1 plus p to the k minus 1. Let us compute this.
Can you slide the page a bit below?
Yeah, sure.
Thank you.
Sorry about that. Yeah. So let us compute this, and hopefully we'll get the p deprived Dirichlet value. Well, let's compute. So it's a half G psi zeta 1 plus p to the k minus 1, which is a half G psi chi zeta 1 plus p to the k minus 1. You remember you can remove the zeta by putting a chi zeta here. That's the second property over here. You can remove the zeta by putting a chi zeta with the power series. So I'm using that property here. I brought the zeta down here, which is a half. This is Iwasawa's first result, main result, chi zeta. And I think there should be a psi here, though I don't have it in my notes. Yes, which is a half. Right here I used, for this step, let's just go back here. Where is the, yeah, so I'm using this result. If you specialize G chi 1 plus p to the s minus 1, right, with k, then you get 1 minus k, this thing. S equals k, and chi to be psi times chi zeta. You get this result. That's the periodic interpolation. And then I'll use this one more time, this result, and I get 1 minus psi omega to the minus k chi zeta. I put the omega minus k before, of p times p to the k minus 1 times an L value. 1 minus chi psi omega minus k chi zeta. Okay, so this is from the periodic interpolation of the Dirichlet L values. I'm using this formula over here, but with chi to be equal to psi chi zeta. So you put a psi chi zeta here, you get a psi chi zeta here, and I move the omega minus k into the center. And psi chi zeta here will give you a psi chi zeta omega minus k. And finally, this is exactly the p deprived Dirichlet L value. So remember, this was the constant term of the P-stabilized Eisenstein series that we started the lecture with. So now we've actually managed to even interpolate the constant term. So this is great. So finally, putting everything together, for psi, which is a Dirichlet character, remember the tame character of the Lambda-adic form, even and let's say not equal to 1 for simplicity, we let, finally we can define a Lambda-adic form, E psi, to be the sum n equals 0 to infinity a n psi x. Notice we had already defined the ANs for n bigger than or equal to 1, but now we've defined the A0 also, and we have this power series here also, q to the n, which is in I psi power series q. Oops, power series q, where I psi is just Zp psi x. So finite extension of lambda. So this is a very important definition. So this summarizes everything we've done today, and by everything we've said above, then, as we saw above, if you specialize nu, so nu is lying over nu k zeta, right? These are specializations of I to qp bar. We're taking x to something. Sorry, lambda. So if you specialize E psi at any nu, any arithmetic specialization for k greater than 2, and actually it works for k equals 1 also, and zeta belonging to mu p to the r minus 1, where r is greater than 1, then this gives exactly the modular form of weight k and character chi, p stabilized 1. Okay, so this example we've done now in complete detail. We completely interpolated the non-constant terms of the Eisenstein series. And for the constant terms, unfortunately, we had to refer to some fairly deep mathematics going back to the maybe middle of the 50s, 60s, I don't remember. Kubota Leopold, to German mathematicians, and then Iwasawa, a Japanese mathematician, who wrote many papers on p-adic functions. And using that fact for the constant term, we could then construct a Lambda-adic Eisenstein series, which interpolates all the p-stabilized classical Eisenstein series. So that's the summary so far. Any questions before I'm actually done, but I'm now going to make some motivational remarks.
Hello.
Yes, go ahead.
Yeah. Hello, sir. That was indeed a very nice and detailed talk. So thank you for that. I have just one question, if I may bother you to go back to page number 10 or 11,
Yes.
where you defined this diamond of D and omega D.
Sure. Here only, yeah, page 11, yes.
Yeah. So I don't know whether this is even legit to ask this question. We can do such, how do you say, we can write any p-adic integer, or if you extend to any local field, you can write any unit in such a way, right?
Unit.
Any unit in the local field can be written like this, right?
Which, like this, which one?
Below. ZP star is...
Yeah. Yes. Yes. This one? This one? Yes, that's correct. That's correct.
Right. So you can write it as some torsion part times some principal unit.
Correct.
Yeah. So can we extend this theory to any local field?
Yes, yes, of course. Of course you can. Yes. Yes. If you have a finite extension of QP and you look at the ring of integers there, OK, then you will get OK star, the ring of integers,
right,
P, the residue field. So OK mod, it won't be P anymore. It'll be some script P, which is the prime ideal, right? OK mod script P star. So that's the residue field star, cross 1 plus script P OK.
Right, that is
So you-
V1.
Yeah, you can write any. This is just a standard decomposition of the units into their torsion and, well, it's not really torsion and non-torsion because this part is not always torsion free. For example, if you did this for P equals 2, then this Z mod 2 star would become trivial, but this would be 1 plus 2 Z2. But inside 1 plus 2 Z2, you have -1, right? Because it's 1 minus 2. 1 plus 2 times -1. So -1 is a torsion element in here. But yeah, you're right. In general, this is a in many cases, this is a decomposition into its torsion and non-torsion parts. But sometimes this can have some p power torsion because it's a pro-p group. So, but yeah, the decomposition certainly exists.
Yeah, no. So my question was, can you
Yeah.
extend this theory to any local field?
Yes, you can. And I just said you can. Yeah.
Thank you.
Yes. Any other questions? Should I go back even more? Lambda-adic Eisenstein series. And this was the first page, more or less, of the talk. Okay, so I'll take more questions in a second. Let me maybe finish the remarks I wanted to make. So this was Iwasawa's theorem, the A0. Then we did a computation, checked A0 worked out well. We put everything together to get the Lambda-adic Eisenstein series. Okay, so some motivation about G psi. So here's a remark. And this is really just extra information since I have 20 minutes and I would have not done it otherwise. But you may ask, what is Iwasawa theory, etc. So this is a good maybe point. Even though this is a course on modular forms, many things in number theory are connected. And it turns out that the p-adic L function is extremely important, and it plays. It describes one part of the Iwasawa main conjecture, which is a quality of two power series. So one of the power series in the Iwasawa main conjecture is coming from the p-adic L function. So let me quickly just recall maybe something about that so that you have some motivation to read Iwasawa theory a bit more maybe. So the Kubota-Leopold p-adic L function, LPS chi. Maybe I won't write notation down because I actually want to even work with the power series G psi, or G chi, maybe I called it. In general, it was G chi, but later it was G psi. So these are related by x goes to 1 plus p to the s minus 1. And actually, there's a 1 minus s here. But anyway, more precisely, this power series plays an important role in Iwasawa theory. So I'll try and do Iwasawa theory on half a page. Okay, so what goes on in Iwasawa theory? So you have the field of rational numbers, Q, and then you tack on all p power roots of unity. Okay. So this is a huge number field. It's not a number field because it's not a finite extension, but it's a huge finite extension of Q, which is built out of all the cyclotomic fields given by tacking on the p power roots of unity. And if you just tack on just the p power roots of unity, then you get something of, as you know, it's a Galois extension of degree p minus 1, and the Galois group is Z mod p star. So this Galois group is delta, which is Z mod p star. And then the remaining part here is this whole extension is ZP star. So this is the wild part, gamma, which is the 1 plus p ZP part. Okay, so these are definitions now of delta and gamma. And then, so this is of course all fine, but one can look at something called the Hilbert class field of Q mu p infinity. It's actually the P Hilbert class field. Okay, so this is the maximal, the definition of the P Hilbert class field. Unramified, so you only want to look at unramified extensions. Abelian, but not just abelian, it's a P extension. So only P is dividing the the order of the Galois groups that appear here. P extension of Q mu p infinity. So this is the P Hilbert class field of Q mu p infinity. So by definition, it's the maximal unramified abelian P extension of Q mu p infinity. Okay, so this is the setup in Iwasawa theory. You have some basic extension, delta cross gamma, Galois group is delta cross gamma, and then you have a further extension, and then delta cross gamma act on this extension. Okay, and then you study the Galois group. Sorry, every time I put my fingers, you can't see anything. Let me come at it from this angle. So you have this extension, the cyclotomic extension, and then you have this P Hilbert class field, and these groups act on these groups. And so you can study this Galois group as a module over this group. And it turns out that the Galois groups are torsion and things like that, and there's some power series that come up because it's torsion, and then you can ask what the power series is, and then the power series turns out to be the p-adic L function. So let me try and make that a bit more precise. That's the Iwasawa main conjecture, which is now a theorem. Then A, which is the Galois group of L over Q mu p infinity, is a torsion ZP delta gamma module. So this is a group ring, and then there's a completed group algebra. Okay. Decompose. So it's torsion. This is the important thing. Decompose A according to the characters of delta. So those are basically omegas and powers of omega. According to the complete list of the characters of delta. Then the Iwasawa main conjecture of Iwasawa theory, which is a theorem of Mazur-Wiles, by the way, and reproved by Wiles for Hilbert modular forms. In Professor Chandrakant's talk, you saw some Hilbert modular forms, so it was reproved by Wiles using Hilbert. Lecture says that once you have a torsion module, so these things, you've got rid of the delta. So this is a ZP power series gamma module. And ZP power series is the same as ZP X. Okay, it's a ZP power series X module. It says that the annihilator, the characteristic power series of these torsion modules these means the A omega I are, I want to say exactly, but I'm a little nervous because I did this S to 1 minus S thing. So let me say are closely related at least the ideals they generate should be the same, but even then there's this S and 1 minus S thing, which is worrying me a bit. It's closely related to the power series G omega 1 minus I. Of X. So for this particular character, at least if I is odd and not 1. Remember when I was 1, this will become omega to the 1 minus 1, you'll get the trivial character. And we were doing this for non-trivial characters, chi not equal to 1. So if you take I to be odd, so that omega to the 1 minus I is even, and you take all possible powers, so you get all even characters except for the trivial one. So it's closely related. Okay, in fact, the ideals they generate should be essentially the same in lambda. And modulo this small check of S goes to 1 minus S. And so this is the importance of the Koboto-Leopold p-adic function theoretically. It describes class groups. Many people study class groups. It basically describes class groups of cyclotomic extensions. Okay, so this is one remark I wanted to make, and maybe I will make one more remark and stop. So tomorrow, well, actually not tomorrow, because it's not Wednesday. Next lecture for me tomorrow means, I think, Thursday. We will discuss general lambda-adic forms in the ordinary setting. So today I didn't make too many noises about this word ordinary. But if you look carefully at all the formulas, so note, today the Eisenstein series EP, E psi that we wrote down, well, even the classical ones. If you look at the EP, let's do the classical ones. K chi. P stabilized ones. We said this yesterday, right? Because it was some divisors d-dividing P, so there's only one in P, then powers, so 1 to the k minus 1, p to the k minus 1, but there was a chi to the p in front, and chi was not real. So you just get a 1 here, 1 to the k minus 1. Right? So this is an ordinary form. So ek chi p is p ordinary in the sense that the p-adic valuation of the pth Fourier coefficient of the form is 0. It's a unit. Okay, and also similarly, the other modular forms, f of x naught 11, if you remember from yesterday, the 11th Fourier coefficient was 1. And if you look at the 11th Fourier coefficient of the delta function p stabilized, it was alpha, which is congruent to 1 mod p. Okay, so all these things are p-adic units. And if we want to construct lambda-adic forms in some generality, then we will be constructing them only for p ordinary classical modular forms. So that is the important thing in the p ordinary setting. So I wanted to say this up front, and maybe on Thursday I will start giving Hida's construction. So in the ordinary setting, these lambda-adic forms were constructed by Hida. And as I said at the end of maybe yesterday's lecture, that you can also think of not lambda-adic forms, they're called Coleman families, but you have p-adic families of modular forms and cusp forms also for in the non-ordinary setting, but the theory is not as nice. When you specialize at weight 2, for instance, you may not get a classical form. And Hida theory says from weight 2 onwards, you always get a classical form. Okay, I hope I didn't get too slowly and lose people, but I'm happy to take any questions in the last 7 minutes.
Hello, sir.
Sir, can you okay, I'll go first. So can you give us any reference for Iwasawa theory, like for a first time reader?
Yeah, sure. So maybe I'll start writing some references down. So for lambda-adic forms, You look at Hida's Blue Book, Chapter 7. And for Iwasawa theory, this is called an elementary introduction to Eisenstein series and L functions, but it looks very scary. It's an undergraduate text, but it's not really even a master's or PhD level text, in my opinion. But anyway, Chapter 7 is quite readable, and you can read it. And then Iwasawa theory, you can look at Washington's book. Iwasawa himself has written several nice books. For example, somebody asked about the structure of local fields, and for example, class field theory for local fields. Iwasawa has a very beautiful book about that, using Lubin date groups and things. So he wrote several books, but he didn't write a book, I think, on his own papers. So for that, you can look at Washington's book on cyclotomic fields. And today I used results from Chapter 5 and Chapter 7, but I think the Iwasawa theory is the stuff I did about the mention about the Iwasawa main conjecture. That's a bit later. So later chapters for Iwasawa main conjecture. And for modular forms in general, I would recommend Shimura's book. There were many questions yesterday, which should come at the beginning, even before all this. Shimura's pink book, pink and black book, Princeton University Press, 1971. No questions?
Yeah, sir. Here,
Yeah.
Karamdeo. I'm Karamdeo.
Hi, Karam. Yes.
Yeah, hi. So just to confirm that, so yesterday, whatever we had sequence of periodic forms,
Yes.
periodic family of modular cusp form, one was due to Eisenstein series and other was this delta function cusp
Exactly.
form.
Yes.
Yeah, so these are particular example of these Lambda-adic forms, isn't it?
That's right.
Yeah.
Those were two particular examples. Yes.
So this whatever are coming from cusp forms, in that this whatever formal Q expansion we take in this Lambda-adic form, that will start from n equal to 1 or something.
Yes. Yes. For a cusp form, the Lambda-adic form, the A0 power series will actually be just the 0 power series.
Okay.
Because all the specializations will be cusp forms.
Mm-hmm.
By the way, there's this theorem in p-adic analysis. It sounds very fancy, but it's an elementary theorem that power series in lambda can only have finitely many zeros.
Okay.
So that's because every power series in lambda is basically a polynomial times a unit power series.
Mm-hmm.
And a unit power series, when you specialize at x, will only give you non-zeros things. But the polynomial can have finitely many zeros. So every power series has finitely many zeros. So if A0 was an arbitrary power series, and after you specialize to all these different k's, you always got 0 for the constant term, that would be a power series with infinitely many zeros.
Okay.
So it would force to be the 0 power series. So you can just start at the beginning and say that a lambda-adic cusp form is 1, where the 0th Fourier coefficient is just the 0 power series.
Mm-hmm. And the other question is this related to this Kubota-Leopold L function.
Yes.
So this we define as a continuous function on this set. Something.
That's right. That's right. Yes.
So, and on the other hand, in the definition of this lambda-adic form, when we are restricting to this lambda, especially
Yes.
f nu, etc., they are classical modular forms. And that side we have the L function related to classical modular forms. So
Yes.
this, in some sense, this in any sense, this Leopold Kubota L function has any relation with those L functions?
Yeah, so far all the L functions that showed up today were all L functions of Dirichlet characters.
Mm-hmm.
There were no L functions. I hope I understand your question correctly. Correct me if I'm not understanding it. But I think you're asking if any L functions of modular forms appeared. Is that what you're asking? Yes. No,
Yeah.
so far there are no L functions of modular forms. There are only L functions of Dirichlet characters appearing, because the constant terms of the Q expansions of Eisenstein series have L values of Dirichlet characters. And that is why only L functions of Dirichlet characters have appeared.
Okay.
And so Yeah, this is a very interesting.
Okay. So
Yeah.
I think I understood now. This Kubota-Leopold function, we have used it completely in constructing. Another one in the remark. Can we go to the page, the last remark, what you were making about Iwasawa theory?
Yes. This one maybe?
Yeah, exactly. So
Yeah.
here q mu p to q mu p power mu p infinity. What
Yes.
we are going, you said this is gamma part.
Yes.
I didn't understand. Means here
Yes.
delta is the Galois group.
Yes,
And other side also
I can
Galois.
explain that.
What is that?
Yeah, so this Galois group over Q is just the Galois groups of Q mu p to the n over Q,
Okay.
right? Inverse limit of them as n varies because you're taking a larger and larger tower, which is the inverse limit over, and this Galois group everybody knows is z mod p to the n star, right? And so if you take an inverse limit like this, you get zp star. And by the question that the other lady just asked me, this is z mod p star cross 1 plus p zp. So this is what I'm calling delta, and this is what I'm calling gamma.
Okay.
So this Galois group has a gamma part and a delta part.
Okay.
Yeah.
And
actually, yeah, the gamma part is more a quotient, even though I split this sequence here. The gamma part is more a quotient because, sorry, so more a submodule. And this Galois group is a subgroup, and this is more a quotient. It's because you have a map from zp star to z mod p star. And the kernel of that map is 1 plus zp. It's just the mod p map. So, but this sequence actually splits, and you can write it as a direct product.
Okay.
Yeah.
Okay. So these are two parts, delta part and gamma part.
Delta part and gamma part, correct.
Okay.
Yeah.
And just the last one maybe is a little philosophical question.
Yeah.
In theory of modular form, so like from modular form side, there may be many questions in modular form which we can answer easily, or we can solve that question by going to Iwasawa theory or something.
Yes, that's the whole philosophy of the Lambda-adic forms. So what he did and Wiles did, they constructed Galois representations attached to Lambda-adic forms. So not Galois representations attached to classical forms, but to Lambda-adic forms. And then they use those to do many things. I might mention one application at the end in my own research where if you have an ordinary form, then the local Galois representation is upper triangular, and you can ask whether the top right shoulder is 0 or not. And it's conjectured that happens if and only if the form is a CM form. It's an open problem still today, but you can tackle this problem using Lambda-adic forms. And Lambda-adic Galois representations, which have nothing to do with the classical world a priori, but of course they have everything to do with it because they specialize to those classical forms. But somehow by making the problem more complicated and working with these Lambda-adic forms, you actually get almost complete information in the classical world in many problems. There's these finite errors which creep in because of the Weierstrass preparation theorem, which I just mentioned, that you get finally many zeros when you specialize. So because of that, sometimes you miss the actual form you're starting with. But in the family, you can often say things with probability 1, what happens. So, yeah, that's the philosophy. Yeah.
Okay, thanks, sir.
That's
That's
a good
all
question.
from my side.
Yes, great.
So I have a question. Having the denominator 2 in this constant term, does it create some problem in having the 2-adic theory, or that doesn't create any problem?
That's a good question. Yeah, so 2 here, I should have mentioned that 2 is invertible. I'll have, if p is odd, then of course half is in ZP, so there's no problem. All these halves are.
Only when it comes to p equal to 2, there might be some additional.
For p equals 2, I'll have to think. By the way, Wiles in his proof of the Iwasawa main conjecture spends many chapters on p equals 2 and deals with it, but I have not done that here.
Okay.
Yeah, it's a good question. I would have to think about that. I'm not completely sure. One thing I can say is that when chi is the trivial character, or in this case psi is the trivial character, you define A0 not to be G psi, but G psi divided by another power series, a very simple power series. And that's to take care of some poles that come up in the p-adic function. You want to get rid of them and things. So that can be taken care of quite easily when psi is the trivial character. The half I'll have to think about.
Thank you.
Hello, sir.
Yes.
Yes, sir. My question is kind of converse for like if we we have this lambda-adic form, then we are getting specialization in classical form.
Yes.
Classical model.
Yes.
Means do we have for every modulo form? Do we have this lambda-adic form?
Very good question. And that is one of the main properties in Hida theory. I'll write a theorem next time where I'll summarize many of the properties of Hida theory. I'll try and sketch the proof of maybe the first property. So one of the properties of Hida theory is there are finitely many lambda-adic forms if you fix the tame level n. Okay, so there are only finitely many families, and of course there cannot be finitely many because things are vector spaces or modules. You can add and multiply by scalars, but finite in a good sense if you take eigenforms and things and normalize things.
Yes.
So there are only finitely many. So that's one thing in the ordinary setting. What you're asking is whether every classical p-ordinary form lives in some family, some lambda-adic form, and that remarkably is actually true. So you can actually include every form in a family. And here is something that's, okay, I'm giving the entire next lecture today. The family which hits your particular form is in fact unique. A unique family hits a particular form. Every form lives in actually a unique family. So everything you can possibly ask for is very nice, as long as the starting weight of the form k is
n to the power p, something like.
The level is n to the power PTR, yeah. Then, but no, but I was talking about the weight. The weight is k. K should be greater than or equal to 2.
Okay.
If the weight is 1, it also lives in a lambda-adic form, but it may not be unique.
Oh, okay. Uniqueness is dropped when k is 1.
Uniqueness is not necessarily true.
Okay.
And, you can look at some of my papers with Dimitrov for some counterexamples. These are well known to people, but not written explicitly. So we have some counterexample to uniqueness when the weight is 1. Then we have some weight 1 form living in 2 different lambda-adic forms. So yeah, and it's a very interesting question. There's a small cottage industry of people trying to answer that for weight 1. How many forms pass through? How many families pass through a particular weight 1 form, etc., etc.
Okay. Thank you.